Okay, good morning. This is Professor David J. De Los Reyes. It's September 16, 2023. The time is 3:40 a.m. Okay, my topic for this session will be a long video format discussion on alternating current machines, and we are now on lesson number 12. Okay, let's proceed. The last time around, I discussed the different circuit diagrams, okay, coming from the primary and secondary till we arrive at the diagram that is something like this, in which we remove already the no load current, okay. So if we try to see the diagram here, the last diagram I discussed the last time around is this one. We are now given the resistance and reactance for the secondary. Okay, the reactance of the primary and secondary. So what I will discuss tonight will be the computation on how to compute for the equivalent resistance, okay, of the resistance and reactance for both the primary and primary and secondary as a single equation. So actually we could, try to make the computation as simpler as it is, not unlike on the previous one. We start from the secondary, then we go to the we start with the secondary, then we go to the primary before we could get the primary input voltage. But in here, it is now straightforward because we simplify the diagram as something like this. Okay, so let us now try to derive the equation on the so-called IR drops and IX drops for both the primary and secondary. So actually the last figure here was actually the last figure from the last discussion. Okay, so we'll now try to compress this one as simple as this one, meaning the resistance and reactance of the secondary and the resistance and reactance of the primary. We'll compress it as to one, it will be something like this. So actually the upper figure is actually referred to the secondary, this one. And the second figure is referred to the primary. So these are equivalent values now. So you can see that there is no more secondary on the second figure. On the first figure, there is no more primary. So we just base our calculations on the secondary values for the first one. And in the second calculation, we refer our calculations on the primary side. Okay, let's proceed with the so-called derivation. So the title of the subject matter for tonight will be Alternating Current Machines, lesson number 12. And the title of the topic is Equivalent Resistance, Reactance, and Impedance of Transformers. Meaning, we got the resistance for both the primary and secondary. We got the resistance for both the reactance for the primary and secondary. And we'll try to compress it as just simple one value. So we could simplify the calculation. And in the simplification of the calculation, we'll start with the so-called derivation. Assume a step-down transformer. So if we try to compute for the IR drops, for the meantime, we use secondary values. Okay, we'll compute for the resistance and reactance as a single value, and resistance and reactance as a single value for both the primary and secondary. So on the solution here, okay, the first product here, ISRS is actually the voltage drop across the resistor portion on the primary resistor portion. right? And the second one, it is still the voltage drop. This is for the primary, no, secondary. This is for the primary, and they are both voltage drops, IR. Okay? So we are combining the resistance of the secondary and primary as a single unit for us to take the single equivalent. Okay? I place it here. The product of ISRS is actually the voltage drop across the resistance portion on the secondary. But how about on the primary? On the primary side, okay, it will still be the product of current times resistance, so this should be I sub P, R sub P. But since our computation for this moment is referred to the secondary, to convert this primary value to its equivalent in secondary, we divide that by A. Okay, that's the reason why there is an A over here. Because we are computing values referred to the secondary, right? We are assuming a step-down transformer, step down. Okay? So we are talking all secondary terms over here. Secondary voltage drop across the resistor. This is now the primary resistance across the resistor on the primary, but to refer it to the secondary, so we could add it, okay? We will divide it by A. Because without dividing it by A, we cannot add it. Why? Because this is secondary side and this is primary side. So we could add it as a value on the secondary side. We will divide this by A. You got it? So they will be of the same, what you call this, classification. This is secondary. This is the voltage drop on the primary, but for it to be added on the secondary, we will divide it by A. Okay? So if we now try to simplify this one, this will be ISRS. Okay? Then we try to replace, we get this RP over A over here, right? And what remains is IP. Okay, let's try to bring out first the equivalent of this IP in terms of IS. Ratio of transformation for a step-down transformer, step down, will be the induced voltage on the primary over the induced voltage on the secondary. And this is actually equal to the secondary current over the primary current. So if we now try to remove this one, okay, A will be IS over IP. Okay? So actually we could compute for IP. IP will be IS over A. So we will replace IP by the value IS over A. So this is now IS over A. Okay? What am I doing? I am converting all values to the values referred to the secondary side. So actually, I eliminated that IP because that IP is actually the primary current, right? But I want the computation to be referred to all the secondary. So I change IP to its equivalent, which is IS over A. So if we now try to simplify this, common factor is IS, open quantity RS. What remains on the second one will be RP, the resistance on the primary side, all over A square. This is now the reason why I am telling you last night there is an A square over here. Where does this A square emanate? It emanates from this, right? Originally, for this IPRP to be referred to the secondary, we divide it by A. And again, the next A came out from the equivalent of IP, which is IS over A. So A times A will be A squared. So that's where the A square emanates, right? There is an A here. On the next substitution, there is an A again, so A times A will be an A square. So this is A square. So the total IR drop, considering the secondary side, it will be IS, okay, times the quantity RS plus RP over A square plus quantity. Okay? We can add this now because all values are already referred to the secondary side. The next one. For the IX drops, it's the same. Am I still on camera? For the IX drops, we'll just follow this one, but we'll replace R by X. We are computing the reactance drop now. So this should be ISXS plus IPXP. The reactance drop on the primary, but since our computation should be based on the secondary, for this to be based on the secondary, we divide it again by A. So this is over A. And this should be equal to ISXS. We combine XP over A. It is this. Right? Then we'll try to replace IP by the value IS over A. Right? This is IS over A. And again, there is a common factor IS. So what remains will be open quantity XS plus XP over A square. Okay? Don't worry with the value XP because we converted this one already as referred to the secondary by the division of A here. Right? And the other A emanates from the value IS over A. So again, there is an A square over here. There is an A square. Okay? So in secondary terms now, okay, the total resistance or the equivalent resistance referred to the secondary should be Rs plus Rp over A square, and the unit is ohms. Where does this one emanate? It is from this one. Okay? Because the single equivalent of this is referred to as the equivalent resistance referred to the secondary. For the reactance, we will just, change the R to X. So, the equivalent reactance referred to the secondary should be equal to XS plus XP over A square ohms. Where does this one emanate? It's from A. Okay? So, instead of writing these two terms here, we just designate as just simply XES or RES. Okay, we just merge it. And if we are given R sub A and we are given X sub A, this is R equivalent referred to the secondary. This is X equivalent referred to the secondary. The vectorial sum is actually the equivalent impedance referred to the secondary. So to compute for the equivalent impedance referred to the secondary, it should be the square of this one. That's the square of this. Then take the square root. It's a right triangle. Okay? It is this one. So meaning to say, if we are given the equivalent resistance referred to the secondary and the equivalent reactance referred to the secondary, we will just use Pythagoras principle here to compute for the value of the equivalent impedance referred to the secondary. So it is actually this one. This value here are actually two resistances. This is two reactances. It is this. The first one is this one. The second one is this one. We just merge it into one. So actually we compress this one and we term this value here as the equivalent impedance referred to the secondary. But we know what is inside. That the resistance is actually the resistance on the secondary plus the equivalent resistance of the primary referred to the secondary, this one. And the reactance is also 2. It is XS plus the equivalent reactance of the primary referred to the secondary, that is XP over A squared. Okay, so these four parameters inside will now just be designated as 2, but we know that RES is actually the resistance on the secondary plus the resistance on the primary referred to the secondary, even this one. Okay? How about the next equation? If you don't want to use the secondary terms in your computations of voltages, you could use the primary terms. So how could we arrive at the primary terms equation? It's the reverse. If this should be primary, okay, we change this to primary, right? Right? We'll get this one. It's this. We are referring it to primary, right? The second value should be the product E squared times RS. You got what I mean? So actually, the second equations under primary terms emanates from the secondary. It's just a manipulation. If this will be primary, the first resistance on the right will be R sub P. It is this. The second term will be the product E squared times, this is secondary, right? Secondary. So the equivalent resistance referred to the primary should be the resistance on the primary plus the product of A squared times RS. It emanates from this. We just manipulate this one. Right? We got this one. Then we change this one to this. It is now referred to the primary. Right? So there is an A square over here as a multiplier. So at least you now know where this A square emanates. Right? For the reactants, it's the same. If this is referred to the primary, it will be XP. Okay, the second part will be the product A squared times XS. A squared times XS. So if we now know REP and XEP, meaning the equivalent resistance referred to the primary and the equivalent reactance referred to the primary, again, you will use the Pythagoras principle. Right? This is resistance, equivalent resistance referred to the primary, and this should be the equivalent reactance referred to the primary. The vectorial sum will be the equivalent impedance referred to the primary. It's a right triangle. Okay? So the second equation, it is the square root of equivalent resistance on the primary, equivalent resistance referred to the primary quantity square plus the equivalent reactance referred to the primary quantity square, then take the square root. The unit is still on. So actually, in the computation of the so-called voltage regulation of transformers, we will be considering voltage drops, okay? And those voltage drops should emanate from this one. If your computation is based on the secondary, you will be using this equation here. If your computation is based on the primary, you will be using this computation. The only unknown here for it to become a voltage drop is actually, because if we try to multiply this by current, okay, this is now voltage drops, right? So these voltage drops are to be added to this, what they call this, primary voltage to attain the required secondary voltage on the secondary. Okay? Oh, I got some annotations here. When a voltage drop is referred to the secondary, divide it by A. Divide it by A. It is this. Our first computation here is referred to the secondary. This is a voltage drop, right? IPRP. This is secondary side. So for this one to be referred to the secondary side, we divide it by A. That's the meaning of annotation number 1. Right? But if our computation is referred to the primary, okay, multiply it by A. If we now refer it to the primary, we'll put A here. We remove this one. You got what I mean? This is primary. This is primary now. That's annotation number 2. Annotation number 1 actually emanates from this. Okay? This is secondary. This is primary voltage drop, but for it to be added on the secondary, we must have to divide it by A. Okay? So this will now be secondary. This will be the secondary equivalent of the product IP RP. Okay, that's it, guys. So in the computation of this voltage over here compared to this voltage here, okay, we must have to include the so-called equivalent impedance, and this equivalent impedance, nice lang camera, and this equivalent impedance are actually these, right? So maybe in a given problem on a transformer, the equivalent resistances and reactances for both the primary are given. So in the computation of the so-called voltage regulation, that may be our next topic. Okay? We should include those voltage drop from the RA and XA equivalents. So our topic for tonight is actually the equivalent resistance and reactance and impedance for transformers. Okay? So instead of working individually for both the secondary and primary like what we did in the first computation, we start with the secondary. We compute all values on the secondary, then we'll refer it back to the primary. Okay? I think you have seen the vector diagrams when we refer it back to the primary. It's a complicated thing. But if we try to simplify it as like this, our computation will be simpler. Okay, this is Professor David Generos Reyes. Good morning from Los Angeles.